Sir, you're live. You can start the session.
Yeah. All right. Thank you. If there are any questions, you can. This is a basically interaction. They cannot speak, right? They cannot speak. So please put in the question chat box your questions. This is almost to the end, the business end of the course. So whatever questions you have, please feel free to ask now on the entire chapters. How many participants are there? I only see two. I only see two. Oh, two participants only. Yeah. So we'll wait for some time if somebody else comes. Up to what point it is taught now, Achintya? So about the lectures. When is the exam? So exam is supposed to be on April 9th. So up to week 12 has been there, so the final week has been completed. Huh? So all the weeks are basically now done. So up to week 12 it has been. No, but the course is ending now, no? Yeah. So by chance are you putting any lecture on the couple cluster or no? Yes, sir. Okay, so there are some questions. It's already in the format. So the first question, I can't see the questions. So the questions is in YouTube. I can read for you, or if you want to. It is in YouTube. Okay. Okay. Tell me. I don't have YouTube link. Yeah. First question, the student asked that in lecture 74 it was mentioned that it is important to calculate the derivative of energy with respect to either nuclear coordinate or some external field in an analytic manner as opposed to a numerical calculation. I don't understand what is meant by analytic calculation and how it is different from a numerical calculation. Yeah, this is lecture 74. Yeah. So I thought there were only 41 lectures or 42. You have the script? The lectures were split. Oh, okay. So yeah. So when you calculate the derivative of energy, so when you calculate the energy with respect to, let's say, nuclear coordinates, they are in the definition of the Hamiltonian. The nuclear coordinates are in the definition of the Hamiltonian. So as the coordinates change, the Hamiltonian changes, the energy changes. So how do you calculate the change of energy with respect to nuclear coordinates? So that is, let's say, one question. So there are two ways of doing it. You calculate for a given coordinates, get a Hamiltonian, calculate energy, change the coordinates, get the energy again, and keep solving. After a few points or few such calculations, you can now calculate. So you have basically energy as a different coordinates. You can calculate now the derivatives numerically. I hope all of you know what is a numerical derivative. If I give you y and x, some values of x, and for those values of x give you y values, then you can calculate numerically. So for example, A simple numerical thing is to calculate y2 minus y1 divided by x2 minus x1. I'm just saying it's a slope. So numerical derivatives are very, very common. Of course, you don't do so simple. This will work only for straight line. But in general, with 5, 6, 10 points, you can try to calculate numerically the first and the second derivative, and so on. But that is very unsatisfactory because you are essentially fitting the points in between. You don't have the results of in between points. With those few points that are given, you are trying to fit and get the analytic derivative. Get the derivative, sorry. However, on the other hand, the analytic derivative is to calculate in the theory itself an expression which gives you delta E, delta coordinates. So energy versus coordinate, the first derivative, I get an expression. On the second derivative, I get an expression. So that is an analytic expression, and that expression is coded now. In the computer program, the expression will be coded, so the derivatives will not be found by numerically fitting. So that is the analytic derivative, and obviously the analytic derivative is more suitable because there I am not fitting in between any points. I'm just calculating analytically through an expression. So once you have an expression of energy, I can calculate the derivative expression, and then you find what are the new parameters, how do you calculate. Those details are probably not there in the classes, and those details you can read later. But I think at this point it is important to know that the analytic derivatives are more desirable than the numerical derivative. So Achintya, can you explain?
I think I would add to this statement is that there are additional advantages in the analytic derivative formulation. One of the advantages is that it is not prone to numerical error. So sometimes your rounding off can lead to numerical error in your derivative calculation. I think more important is that for doing numerical derivative, you need to do number of single point energy calculation as many number, twice the number of field you are calculating. For give me an example. If I have a n atomic system, so it will have 3n coordinates. So I will at least need to do 3n minus 6 into 2 numerical energy calculation for doing this purpose. So the computation cost is much more higher. So suppose I have a 10 atomic molecule, that means I have to do 3n minus 6 will be 24. So I need to do at least 48 calculations. Whereas if I do an analytic calculation, the computation cost is generally twice of the single point energy calculation. So you save a lot of time to do analytic derivative calculation. They are more, so there are two advantages. Analytic derivatives are more accurate, and secondly, they are much less time consuming to calculate.
So these are two different points. One is numerical cost, but even if the cost is similar, would have been similar, the numerical calculations are not very desirable because it still gives a fitting. These are basically like interpolation between certain points and you calculate derivatives. So mathematically, you interpolate, extrapolate with certain curves. People do a lot of fitting with different algorithms like Newton-Raphson and so on, least square method. You can also fit. But the important thing is that they will still be fitting. You can do those fitting and generate more points, but they will still be fitting. So that is why numerical methods are unsatisfactory. But what Professor Dutta also mentioned, that if your number of variables is large, then computational time will also increase in numerical. For both the reasons, analytical techniques are more desirable.
So the next question is about MCSF. Student asked that it was said in lecture 74 that we select the configuration for MCSCF by considering the near degenerate orbital as active. So student has a question that what about the remaining occupied orbital that were not considered active? Are they ignored for the MCSCF calculation?
So the active orbitals are those orbitals which are nearly degenerate or very close lying, so that the state of the system is more likely to be such that those active orbitals are occupied by those active electrons. So for example, I can give you an example, let's say 1s2, 2s2, very simple example of beryllium atom, but 2s and 2p are very close by. So if you have two electrons, they can be either in 2s2 or in 2p2, even if it is singlet. But the 1s orbital, which is core, is much lower. So you can always assume those two electrons are in 1s. and you can do configuration only within the active orbitals. That suffices. So it is indeed true that those orbitals which are not active do not participate. They do participate, but they are constant in all the configurations. It's not that we are freezing them. These are two different things. They are there, but that part of the inactive orbitals are always occupied by those electrons, inactive electrons. So we only do the active orbitals because they are close by. Those configurations mix among themselves more than the others. So that is the meaning of this. Yeah, if you want to explain further.
So if you want to see the MCSF in an alternate way, you can consider the MCSF is a method where your full CI is actually done within the active orbitals. And rest of the orbitals are treated as a normal Hadrikov orbital. So you have a two-level of optimization. At one level, you are optimizing the orbital, that is the standard for the active and inactive orbital. And at the same time, you are doing a full CI calculation within that particular active space. So there is full level of orbital optimization which is going on. And because of this, you can actually cheat an MCSCF code to do full CI calculation. So sometimes what people do is that if you take all the electrons and all the orbitals as active, that will lead you to a full CI calculation, which will, of course, it's a very bad way of doing a full CI, but it will still gives you a full CI calculation. Of course, what you miss here is that there is no correlation effect for the orbitals which are not active. So that is somewhere that they are not correlated in an MCSCF calculation. So you have to do some post MCSCF, either a perturbation or a CI, to have a correlation treatment for this kind of orbitals. Okay, so the next question is that the student says that I am unable to fundamentally understand the concept of intermediate normalization. So student said that, could you please explain this concept again and tell us why it is necessary and what purpose does it achieve in that?
Yeah. So first of all, it is not necessary. Let me first tell you. It is only a convenience. Now, let us say that I have two configurations. Two determinants, forget about the rest. One of them is very large, another is very small. So let's say I have a phi 0, one determinant, another is phi 1. In normal configuration mixing, you will do C0 phi 0 plus C1 phi 1. Incidentally, phi 0 and phi 1 are orthogonal to each other. So that is usually what we do. Normally in CI, you will do C0 phi 0 plus C1 phi 1. But as you know, that any wave function can be multiplied by a coefficient. So the same C0 phi 0 plus C1 phi 1, I can divide by 1 by C0. I am allowed to do that, right? So then my C0 phi 0 becomes 1 times phi 0, and the rest becomes C1 divided by C0 phi 1. I can now call C1 by C0 as another new parameter, let's say C. So it becomes 1 plus C phi 1. This is the intermediate normalization, where the main function phi 0 has a coefficient 1 and other functions have some coefficients 1. In doing so, what you lost is the normalization of psi. Because if you had C0 phi 0 plus C1 phi 1, I can normalize by saying that C0 square plus C1 square equal to 1, right? That is the normally normalization that you do. In this case, you cannot do because the first coefficient has already become 1. So even if there is a small value of C, which is C1 by C0, it will become 1 plus C square, which is greater than 1. Okay, so you cannot normalize it, but you can always get that from the intermediate normalized function, a normalized function by the reverse process. Because it is 1 plus C square, the normal normalization, I can divide by 1 by square root of that and get a new coefficient for phi 0 and a new coefficient for phi 1. So I can keep doing it. So there is no new physics that is introduced, but there is a convenience because I get rid of C0, the first term, by setting that C0 equal to 1. So some of the equations become simpler. So you will see the correlation energy becomes Hartree form plus something. Otherwise, if there is a C0, then it would have become C0 into Hartree form plus something. So that would be more difficult to say what is a correlation energy. Here it is Hartree form plus something. I hope you remember, you understand. If my coefficient has C0 phi 0 and that is the Hartree form, then if I do psi a psi, then C0 Hartree form will come from phi 0, but it will be multiplied by C0 square. right? So I cannot now identify what is electron correlation energy, because correlation energy you subtract Hartree Fock. But if I subtract C0 square Hartree Fock, that is not correlation energy. So again I have to rescale it anyway. So that is the reason intermediate normalization is very convenient to do that. So all electron correlation problems which are defined as E0 minus E Hartree Fock or E Hartree Fock minus E0 depending on your sign convention, it is convenient to use intermediate normalization by setting the initial term C0 as 1. But the only thing is that you lose the normalization, so the function is no longer normalized unity, but you can always renormalize whenever you require. But for CI equations, it is much simpler. CI and eventually couple cluster, perturbation everywhere, this becomes a very convenient tool, the intermediate normalization. Otherwise, of course, you are right, it is not necessary. I can do away with that. It is also, just the expressions become simpler, and it certainly does not introduce any new physics. Both are correct. Yeah, Achintya, you want to say anything?
No, I think this is what you. So Satkar further asks that even though the equations become simpler, we still have to renormalize the overall wave function at the end. Is it true or not?
No, it's not necessary. If you want only total energy, then it is not required. If you want wave function, even if it is unnormalized, intermediate normalized, you don't get any new physics. So you don't lose any physics by intermediate normalization either. So you do not have to do it. If you are calculating probability at some point of time where you require normalization, you have to just remember that you have to divide by psi 0, which is 1 plus all this C square, and you can still get everything that you want. So, yeah, there is no reason that you have to renormalize to get psi. For a specific purpose, you want to get a normalized probability, then you have to do it. But you can always divide by the norms and get the norm square, and by the norm, sorry, not norm square, by the norm, and you can get back the. So it is not a big thing, but the main advantage is that when you calculate energy, that is our focus. It becomes simpler, and it's also simpler to identify the correlation energy. That is the main emphasis why intermediate normalization has been used, or you will see for the correlation problem. So that is where it is required. In many old textbooks of CI, the intermediate normalization has not been used. So CI actually often they do it C0, but then in energy C0 square remains, and it's a matrix diagonalization. The C0 square, C0 explicitly appears. As soon as the intermediate normalization, that C0 becomes just 1. The rest of the variables appear. So I think that's a difference between how we are setting up the equation. But in couple cluster, intermediate normalization is always used. We have not done that, but it is always used. And even in perturbation theory, it is usually the intermediate normalization that is used. In the CI context, both have been used. The older CI used to use C0 everywhere, CL, phi n. But today, they use the modern language. And as I told you, psi is not normalized. But if you take overlap of psi with that main determinant, for which the coefficient is 1, that overlap value is 1. Because all the other determinants are orthogonal to that. So psi phi 0, if psi is the overall wave function, phi 0 is the main determinant, phi 0 psi is going to be 1, but not psi psi. Okay? And of course phi 0 remains to be 1. This determinant is individually normalized. You want to add anything?
I think also the thing is that in CI it has another significance. So CI is not only for ground state, it will also give you excited state. And this C0 actually gives you the contribution of the ground state and wave function into the excited state. So what happens is that sometimes you solve it and then renormalize to get the C0 contribution. But most of the time it is very convenient that if you have the C0 to be 1, then at least for ground state the picture is very clear. You understand what is Hartree Fock and what is the contribution beyond Hartree Fock. And if for every property and energy, you can always write it as a Hartree Fock contribution plus a correlation contribution. So that makes things very clear in your mind. Of course, you can renormalize and get it the full normalization, but generally that is never used for grounds. And anyway, for the energy, you really don't need the normalization to full normalization. Any more questions?
So when is the exam you told me?
It's 28.
Questions? Yeah, if you have any further question, anyway, I wish you all good luck for the exam, for the NSEM exam, all of you. And I hope the course has been useful to those who wanted to learn advanced quantum chemistry at least.
Sarthak asked a question that while reading about MQ2 calculation in old-type group library, I came across an approximation called RIMP. Can you talk about what this approximation is? Dr. Pal?
Yeah, what is it? I didn't.
So he asked for RIMP.
RIH?
RIMP2.
Oh, RIMP2. Yeah, so that is basically a restricted MP2 in some sense, where you don't. Is that an active space MP2?
No, the resolution of identity.
Oh, okay. No, sorry. So, resolution of identity is only expresses the energy in a very simple manner. So, for example, if I do a summation over all the determinants, ket and the conjugate, it's equal to 1. That's identity. So, when you are doing the virtual summation, you often use that resolution vector within the orthogonal subspace, the virtual subspace, and that's, you don't have to keep writing the phi I and then another phi I, sum over I, you can just say R. So that simplifies. So for example, you have just V or not V. Okay? And that is a resolvent actually. Finally, if you include the denominator, also it becomes a resolvent. Otherwise, it just becomes summation of the virtual space. So it's very simple to write the perturbation expression. Once again, it does not create many new physics. I must say that. It is again just a simple way of writing. But I thought you were talking of some restricted space MP2, that's the new physics, where you actually restrict the virtual orbital themselves. In MP2, people do that by doing a very quick, dirty calculation about the coefficients. And you can do by with perturbative estimate and then select only certain parts of the virtual orbitals and remove them for all higher order perturbations. By second order perturbation, or you can actually do a quick calculation which virtual orbitals contribute. So that is completely different. But if you are only talking about the resolvent is just a very nice way of writing the energy expression. And once again, does not bring necessarily any new physics, because the expression becomes otherwise very, very long. There are so many sums of the excited states, intermediate sums, that gets simplified.
Santak further asked that if he tried to do a large calculation without RI approximation and the job actually crashed. Okay, so Santak, what actually happens is that you have read about this force-centered 2-electron integrals, right? So in this RI approximation, these force-centered 2-electron integrals are actually decomposed as a product of two 3-centered 2-electron integrals. Now, because from 4th center you go to the 3-center picture, so your storage requirement becomes smaller and you can calculate them very fast on the fly. So you're actually to totally remove the bottleneck which comes from the integral storage cell. For a normal MP2 calculation, you have to store these 4th center 2-electron integrals in a molecular orbital basis. Here if you use RI, because you can decompose them into 3-center 2-electron, so one order of magnitude less. So you can actually calculate them very fast and you never actually need to store them. So if you use RI approximation, the calculations are much faster and generally the error introduced is very small and they are very systematic. So they cancel out when you calculate energy differences. So MPT calculation is generally always done with RI. Okay, Sarthak wants a DFT course from you, Dr. Pal.
Well, that has to be a separate course, unfortunately, because this was on the ab initio. I actually had a DFT course. I conducted that in ISAC Kolkata, but unfortunately, I had the video recordings also, but that has not gone in the NPTEL platform. But it can go as a very small course. It is not a very large course. It was about 8 to 10 lectures, I think, if I remember. So those videos are with me. But maybe I will retake most of the videos and try to put it in some open platform, either YouTube or NPTEL. If NPTEL is interested, I will go through another NPTEL course. But indeed, yeah, DFT is, this modern quantum chemistry DFT is very, very important because most of you I know are using DFT. But I can tell you DFT actually can be more difficult than the wave function quantum chemistry because there is a great philosophy in DFT. When you are writing this in DFT, that everything is written in terms of density, energy, which is only a one particle density matrix and its diagonal terms, it always raises question, how can you write? And how can it be exact? So that there are fundamental questions, but it is of course exact because Weinberg and Kohn showed that it is possible to write, but Weinberg and Kohn could not derive the functional. Possibly the functional does not exist, we don't know. I mean, nobody can derive. I wouldn't say it does not exist in the right word. Even if it exists, there is no way to derive. So Weinberg and Kohn theorem is an existence theorem based on which DFT is there. And then the kinetic energy part, particularly for molecules and all, nobody could write in terms of density. So there are early exercises where for atoms people wrote rho to the power 5 by 3 term as the kinetic energy term, but it didn't work out, particularly for molecules. So people had to bring back the orbitals anyway, like Hartree-Fock orbital, n orbitals. So they become what is called Kohn-Sham DFT. So those who are interested, I must say that today what we use in all the software is Kohn-Sham DFT, where there are n orbitals. From the n orbitals, we construct density, and then with that density we write Coulomb term is exact, but the exchange term and the correlation terms are approximate. So that is why you will find DFT, a lot of exchange correlation components, which are like B3 leap and so on. Yeah, so that is where it becomes complicated. And the fact that I cannot write the kinetic energy part directly in terms of density is a serious problem. So I always tell that if anybody can find a density, a kinetic energy as a direct form of density, analytical form, that will be a great work. Whether it will get Nobel Prize or not, I don't know, but it's quite likely to get Nobel Prize, according to me. Exchange and correlation functionals, of course, have to be improved. They are being continuously improved, as you know. Minnesota functionals, double hybrids, all kinds of functionals have come. But the kinetic energy remains a major bottleneck because of that we have to bring in the n orbitals, n spin orbitals, just like in Hartree-Fock. So the equation somehow becomes like Hartree-Fock equation, except the Fock operator is now Kohn-Sham operator, including the approximate exchange, approximate correlation. So I think those are very interesting. And when you do these n spin orbitals, even kinetic energy is approximate. You can't have an exact kinetic energy. So the kinetic energy error is also put inside this approximation of exchange and correlation. So it's a quite an interesting and involved exercise. So those who are interested should start with the Parr and Young's book. I can recommend, there's a book by Parr and Young. I think it is called Modern Density Function. I don't know if anybody remembers Modern Density Function Theory. It starts with what is called density matrix theory. It's very important to understand density matrix theory, which is kind of exact. And then it goes into the density functional. It's a very good book. Yeah, I will at some point of time, I also, because there is a lot of, the institute where I am, the institute where I was, there's always a demand that I take a DFT course. So in ISAC Kolkata, when I was there, I took a DFT course. It was an evening lecture, so about 8 to 10 lectures that I said. They are already videoed, but I think I need to refine that, and then I can approach the NPTEL for another course. I will do that in due time. So this is a good suggestion. I also have that in mind, because so many of you are using DFT, and most people do not understand DFT properly. So I also want to do that course. Yeah, sure. But this was mainly on wave function based course. Okay. The question that I always ask is many-body method. I hope all of you know at the end of the course what is a many-body method. And I must say that what is a many-body method was actually done in a very, very famous article in 1971. Yeah, I think 1971, Annual Review of Physical Chemistry, when somebody called, I think Carl Fried, who actually asked this question, how many bodies make it a many-body? 1, 2, 3, 4, and so on. The actual answer is infinity. So when you say many-body method, it means that the methods which scale properly as the size of the system goes to infinity. And you will find MP2 wave function, Ci has a problem. I think I have explained to that DCI is only square root of n. So DCI energy per particle limit n tends to 0, it becomes 0, which is wrong. Smaller particle, you don't see that. But MP2, which is called MBPT actually, has the right many-body method. Look, the couple cluster is also similar. So this course is about many-body methods, which scale correctly at the infinite limit. So I always ask the question, is DFT many-body method? Those are very interesting questions. And when can DFT be non-many-body method? So when we teach that, we'll see that those are many of the interesting points, because of course if energy doesn't scale properly as n goes to infinity, you'll have a problem, a large size particle. And DFT always targets the large particles, for large systems, right? Not particles, large systems. That is when I use DFT. So it is more important that DFT remains many-body, which means the size extensivity, size consistency that I have discussed in this course are all retained in the DFT. And that is not very easy, particularly size consistency. But I hope you remember that size extensive are those where energy is proportional to n. But size consistency is not guaranteed by that. For a size consistency, the reference space, whether it is single determinant or multi-determinant, they must separate correctly. The reference space itself must separate correctly, fragment correctly as the interaction goes to infinite limit. Then of course the rest of it will ensure that if it is size extensive, it will ensure that it remains size consistent. So if a theory should be size extensive and size consistent, then that is the most ideal case. But it does not always happen. Even in couple clusters, single reference couple cluster, we have not couple clustered here properly. It is a proper method for many-body, but if the Hartree form itself is not size consistent, does not separate properly, then even couple cluster will not be. But multi-reference couple cluster will be, because I can choose the multi-reference such that that separates correctly, then the couple cluster part will guarantee. So same thing will happen with MR MBPT, multi-reference MPT or MBPT3, whatever you call it. So I think these are quite difficult questions. I wish in the NPTEL online platform, one can only do so much, but if it is live audience, certain things can be explained even better. So I sometimes feel that I should take a course on the live audience. And that's what I did. I said, Kolkata, there were students who are online, but they are live. I hope you understand. So I was teaching with iPad, and I could explain at that time, rather than this going like just a separate one, and then the live sessions are often conducted after a few lectures. So there's a little bit of a difference. So I will see how I can conduct DFT based. I will talk to the NPTEL team, and if I can make the lectures live and have the live sessions right during the lecture, that will be the best thing. Anyway, thank you for the suggestion.
I think Satak also asked that, does it mean that many-body method has to be smaller size sections?
Many-body methods?
Has to be always size sections.
Yes, many-body methods are size extensive, no doubt. But as I said, the fragmentation is different from being many-body, because there the separation space has to has to also separate properly, the reference base. Yeah, indeed, they have to be, otherwise, if E is not proportional to N, then of course you can see that an infinite particle limit, energy per particle will not come out right. So you always have a prefactor, the prefactor remains as energy per particle. Okay, and the rest will cancel out per particle, N will cancel out. But if it is N to the power anything less than 1, you will see that the energy per particle will simply vanish. It will become 0. As it happens in DCI. DCI is the same problem.
There are no further questions. Then I think we close it here. Thank you for participating in the course.
Yeah. Second, thank you. Yeah. Thank you for good luck. Thank you for participation in this course and good luck to all of you. This was an advanced quantum chemistry. I have actually in mind, let me tell you, also a basic quantum chemistry. This is a little bit advanced. So starting from postulates, I did that here also, but starting from postulates to particle in a box, Ehrenfest theorem, etc., etc., and Hartree-Fock, properly doing Hartree-Fock, and maybe helium atom, perturbation theory, etc., and stop there. So that will be like a basic quantum chemistry course, which I teach, but I have not videoed that. This is an advanced quantum chemistry where the basics are also taught in the beginning, I agree. So that is also one thing that I have in mind. Another is DFT. Another is certainly DFT, I have in mind. So I will see whenever I get time, I will try to do. If there is sufficient interest among the participants. And
Is it here?
yeah. So thank you very much for participating in the course and good luck for your exam. Yeah. I hope it has been useful to at least many of you. Thank you.